Mechanical engineering begins with a fundamental challenge: generating power in one location only to require it in a completely different, misaligned location. A gear acts as the physical bridge between these points, providing the connection necessary to transfer motion and force from input to output. Beyond simple transfer, these components function as control mechanisms, adjusting speed and torque to reach the highest possible level of machine efficiency. A design of any gear system relies on two mathematical variables: the spatial alignment of the rotating axes and the specific load requirements of the physical system. Engineers solve these spatial problems using 7 foundational gear topologies. In this framework, the physical geometry of a gear tooth is what dictates the entire flow of mechanical power. We begin with the most basic scenario. 2 axes of rotation positioned perfectly parallel to air is the primary mechanical solution here. The teeth are straight and parallel, matching the orientation of the shafts exactly. This design is best suited for direct power transfer, where the load is relatively light and precision is a requirement. These are the gears found in clock mechanisms and standard machine tools. Because straight teeth engage simultaneously, they create high stress points that fail under heavy loads. To manage this, the teeth evolve into a helical gear. Angled teeth distribute pressure gradually, instead of hitting all at once. This specific morphology allows the system to handle significantly higher RPMs and much heavier mechanical burdens. You see these used in car gearboxes and heavy industrial machines, where power demands are highest. High-performance motorcycle engines rely on these helical gears to maintain complete control over extreme torque and rapid speed changes. Curving the geometry of the tooth allows engineers to solve for catastrophic stress without needing to change the orientation of the shafts. The spatial problem changes when the rotational axes are no longer parallel, but physically point toward each other until they intersect. Parallel teeth cannot mesh at a corner, causing standard spur and helical designs to fail in this topology. A bevel gear solves this 90-degree intersection. The gear faces are angled into a cone, which allows the rotational power to turn the corner. This is how milling machines and pump mechanisms redirect power perpendicularly. But axes do not always meet at a perfect right angle. For non-standard intersecting angles, engineers use the angle gear, a specialized variation of the bevel design. These are necessary for complex automotive differentials and the internal machinery of marine vessels, where space is constrained. Creating an angled face and the gear teeth allows rotational power to bridge these different geometric topologies. The most complex 3D challenge occurs when shafts cross paths but do not intersect, passing one another with a clear physical offset. This offset is bridged by the hypoid gear. It uses conical traits and twisting teeth to reach across the gap between the shafts. This design allows for massive gear ratios and very high load tolerances because more of the tooth surface is in contact at once. This makes hypoid gears the standard for heavy-duty car differentials and industrial gearboxes. Beyond shaft alignment, some systems require an extreme transformation of high-speed rotation into raw torque. The worm gear uses a screw-like cylinder to drive a wheel. This screw morphology creates a massive reduction in rotational speed, resulting in a surge of pushing power, or torque. Because this system is secure and slow, it is used in bench drills, lift systems, and cranes to move heavy loads safely. Offset topologies and extreme torque requirements lead to the most radical departures from standard wheel-like gear shapes. Not every output is a spinning wheel. In many cases, engineers must move an object along a straight, linear path. This is the rack and pinion system. A small circular gear, the pinion, meshes with a flattened toothed track called the rack. As the pinion rotates, its circular motion translates directly into linear movement along the track. This translation drives car steering systems, precision ATM mechanics, and railroad track switches. By flattening the gear into a plane, rotational power can push and pull objects through linear space. This analytical grid organizes these mechanical components into a strict taxonomy of physical forces. We see straight teeth for parallel tasks, angled teeth for intersections, and rack configurations for linear movement. At the same time, curved teeth handle heavy loads, while screw designs provide the necessary torque for heavy lifting. Every gear functions as a specific, predictive geometric solution that bridges the physical constraints of space and force.